In 1.2, you are going to learn your first two methods of how to factor. And factor is basically the division part of the polynomials. What you worked on in section 1 was the multiplication part. We only spent one section on multiplying polynomials, and we hit everything. We hit binomials and monomials. We hit binomials times binomials. We hit binomials times trinomials. And even a binomial times a binomial times a binomial. Those are the ways that we touched upon it in section 1. In section 2, we're learning the first two methods of factoring. Factoring is a way to divide polynomials up into smaller groups, into groups of multiplication. And there are several different methods you are going to learn. So much so that that's why we have a section 2, a section 3, a section 4. Like when I click this little button right here, I know that we're going to learn two different methods here, a method here, a method there, a method there, and a method there. So we have 1, 2, 3, 4, 5, about 6 different methods you're going to be learning throughout this unit on how to divide. Multiplying was a lot easier compared to dividing, but it's just working backwards. So let's move back here. First method we're going to learn is something called Gcf Factoring. It is the most commonly used factoring form throughout all the sections. Each of those additional sections will still use Gcf Factoring. It's the first one we always try. It is the opposite of the distributive property. We're going to factor out the largest coefficient and the highest common degree. I like this word common. I think about what I have in common with students. Most students and I have in common the love of donuts. I love donuts. Most students are big fans as well. You know, we have that. Now, what may vary amongst us is which donut is your favorite. Mine just so happens to be, when I'm going small, maple bars. When I'm going big, apple fritters are the #1 donut in the world. If you have not had an apple fritter, you are missing out. Okay, with that being said, Gcf Factoring is where we are going to basically divide by something. I want to find the largest number that goes into both of these two things. The largest number that goes into number problem 2 is what goes into 8 and into 28. Let me see. 2 goes into 8. 2 goes into 28. Does 4 go into both of these? Does 6? Does 8? Does 7? What is the largest number that goes into both? Say the number out loud.
4.
Wonderful. The highest common degree of variables. Does this term have a letter D? Does this term have a letter D? Yes, they both do. This has 3 factors of D. This has 2 factors of D. What do they have in common? It's like saying this person over here likes 2 different kinds of donuts. This person likes 3 different kinds of donuts. What do they have in common? What do they both share? How many do they both share? They share at least 2 of them. When you divide, when you factor out this GCF, this is called the greatest common factor of both of these two terms. You put it in front of your parentheses, and then you figure out what has to go here for your first term, plus what has to go here for your second term. In other words, 4d squared multiplied by what gives you the 8d to the third? What do I need here? 4 times what gives me the number? And the letter. Because this would then multiply to be that first term. And then plus 4d squared multiplied by what would give you 28d squared? What number?
7.
Do you need any additional variables? And what you can always do is you should be able to go this GCF multiplied by this to get you your first term, this GCF multiplied by the second term. You can check your answer by the distributive property. The other thing that I always do, okay, this is my final answer. 4d squared multiplied by, in parentheses, 2d plus 7. I look in the parentheses and I say, is there a GCF of a 2d plus 7? Can I factor anything out of that? If you cannot, you have used or found the GCF. If you can, this was not the GCF. That's a good double check. Number 5. This is how hard it gets. Not how hard, but how big they get. 108, 60. Those numbers are kind of big. So when I look at 108 and 60, 108, I need to figure out what goes into 108. Okay, well, I know 12 goes into it. 12 times 9. If you ever get stuck and you're trying to figure out what your GCF is, I'm going to show you a quick technique. I know that a 12 goes into both of those because 5 times 12 is 60. I did not know what 109, what goes into it. I had to use a calculator for that. If you ever get stuck, you can always turn it into prime numbers. 2, 54, thank you. 6, 9. And what you could see is 2 times 6 is 12, and 12 goes into both of those. This would break down into 3 times 3. This is a 5. They do not have that in common. You can look for the highest thing they have in common. They have a 12. You can think of the most amount of whatever the prime number is that goes into both. I'm going to go with the 12. 12. How many S's do they have in common? What's the most amount I can take out from both? Say it out loud. I agree. Do they both have T's? What's the highest amount of T's I can take out of both? Good. They have that in common. Then you put parentheses. 12 times what gives you 108? Do I need any more S's for the first term? Do I need another T for the first term?
Yes.
So it's 9T, minus sign, minus sign. 12 times what? What's the coefficient?
5.
How many more S's do I need?
2.
Do I need any more T's?
No.
There's your answer. You should look and see. 9 and 5, nothing else can come out of that. A T and an S squared. There is no additional GCF, which means this must have been the highest common factor we could have used. If they get stuck, use a calculator, break it apart, look for the GCF that way. Last example I have is just something a little bit bigger. Sometimes there are 3 terms, a trinomial. Sometimes there's already a GCF out front. If there is, then you leave that Z in there and you start looking for numbers first and foremost that go into all 3 terms. Is 3 the highest number?
Yes.
Because 6 cannot go into 27, right? So we have to use 3. Is there a common variable that's in all 3?
Yes.
How many of the x's could we also pull out?
2.
Okay, because I like to write my things in alphabetical order, I'm going to put 3x squared and then keep that z right there in front. 3x squared z. If you're wondering, like that z being in front still multiplies that GCF we just factored out. In my mind, I'm kind of ignoring it because I'm going to do 3x squared times what gives me 6x to the fourth. 2 what? Okay, keep going. Plus what? Plus what?
6.
And what we could do is look to see if anything else goes into here, which it doesn't, and we're going to stop right there with that problem. That method is called Gcf factoring. If there's something in front, leave it in front. Don't freak out about it. The second type of factoring method that you are going to learn is something called difference of squares. Difference of squares only works when you have a perfect square subtracted by another perfect square. A positive perfect square and a negative perfect square, this will work for. When you factor a positive something squared minus or subtracted by another one that's squared, it will factor perfectly into two binomials, one with the plus sign, one with the minus sign. If you don't believe me, you can check this by foiling. A times A is A squared. The outside is a negative AB. The inside, I know some of you might think of this as BA, but just to make it match, I'm going to write it as AB since I can write multiplication in any order by the commutative property of multiplication, minus B squared. What happens with a negative AB and a positive AB, you will notice that the O and the I cancel out. A difference of squares always factors to a positive and a negative factor of the square roots. All I have to know is what's the square root of the first one? Put that there, put that there. What's the square root of the second one? Put that there, put that there. Put one plus sign, one minus sign in the middle. It will work when you FOIL it. Let me give you an example. Do you know what the the square root of 36 is? Do you know what the square root of P is? Or P squared, I should say? Do you know what the square root of Q squared is? So we know that this is a perfect square, this is a perfect square, and it's a difference of squares. This only works for a difference of squares. I can figure out what's the square root of this, what's the square root of that, and then I'm going to put that in the front of my parentheses. You told me what the 6p? The square root of Q squared, you said, was Q. We're going to have one addition group of the square roots. We're going to have one subtraction group of the square roots. That's what it's going to factor to. And if you don't believe me, FOIL it. This times this, does it equal the 36p squared? This times this with the negative on the O and a positive on the I for the outside and the inside, those will just cancel out. And then a positive times a negative is a negative. It works, and it works every single time. How does this get harder? It gets harder when you put both methods together. Meaning, what if you have to do a GCF and the difference of squares? Let's look at number 15. Whenever you see the words factor completely, a lot of times that is going to be a hint to you. Let me put over here, hint. When you see this, hint, it usually means you're going to have to do more than one method. A lot of times I've read the person who wrote all these worksheets and quizzes and tests and stuff, they write factor completely almost always. Whenever I read that, it means that there's more than one. You're going to have to do something twice. It's like, oh, keywords. So I look at this, not a perfect square. 36 is not a perfect square. I cannot use the difference of squares right now. Is there a GCF? Let's start off with a GCF for number 15. Let's see if we can factor out a number that goes into 36 and to 64. Right now, I see a 6 times 6. 64 is a 4 times 16. 4 times 4. So that must mean that there is a 2 and a 2 in here. And that is a 2 and a 3 and a 2 and a 3. I'm pretty sure we're going to be able to factor out a 4 from both of these things, right? 4. Do they have any x's in common? How many can I pull out? Do they have any y's in common? How many can I pull out? Okay, now if I factor out a GCF of 4xy, the number is going to be what for the first term? How many more x's? Any more y's? Minus. If you don't know what 64 divided by 4 is, it's 16. Any more x's? Any more y's? How many? Good. Do not stop after you've done the GCF. Factor completely usually means you're going to use more than one method. If you look at this, there is no more GCF, but is this a perfect square? Is this a perfect square? If so, we break it apart. And if so, don't forget that there's a GCF in front. What does that mean? That means we go like this, and we're going to break. Let me do this in blue over here. I'm going to put this part in blue. What's the square root of 9x squared? That's what goes in front of both of those parentheses. You just take the square root. What's the square root of the 16y squared? That's what goes in the back. We need one group of addition, one group of subtraction. That's the GCF. Oh, don't forget about the GCF, as I should say. There's still a GCF out front. Factor completely basically means keep factoring until you cannot anymore. And sometimes you're going to use a GCF and a difference of squares, just like number 15. And if you ended up getting this answer, it is not full credit on a test. This is like a -1 or a -2, depending on the other methods that you could do afterwards. Making sense? 2 more examples, then we'll be done. Is there a GCF of number 19? Okay. If you factored out a GCF of a 2, what's left? K to the minus what? And I chose this one because you may not see it. You may not think of this as a perfect square or difference of squares. But this is, I know what the square root of 16 is. I also know what the square root of k to the 4th is. If you're not sure, think of k to the 4th. I'll write it over here. Isn't that the same thing as k squared to the 2nd power? So the square root of k to the 4th is k squared, which means I still have the GCF. I'm going to break this apart using the difference of squares. I'm going to put the k squared here and the k squared there. because this times this will give me k to the fourth. The square root of 16, 4 and 4. And then I need to have one group of addition and one group of subtraction. It only works with a plus and a minus. Have I factored it completely?
No.
Oh, can I keep going?
Yes.
Is this a difference of squares? Can this piece that I'm pointing at factor further?
Yes.
Now, what about this piece? Can this piece factor further?
No.
Is it a difference of squares? No, it's an addition sign. Perfect square, but if it's a plus sign, it cannot factor further. Until we get to second semester, then I'll show you how, but not right now, okay? But when you're here, difference of squares, we can factor this piece only. So what do? We leave this alone, we leave this alone, and I can factor that piece into two groups. The square root of k squared is k and another k. Square root of 4, 2 and another 2. We need one group of addition, one group of subtraction, and that is factored completely. Sometimes it gets into like stuff like that. Josh.
What is the fourth root? Somehow.
We do not have a method of factoring using a fourth root at this point. We're learning difference of squares and we're learning GCF factoring. The last example I have for you is one of the word problems. That's number 23 in your homework. It says there's a circular garden in the middle of a square garden. Here's the circular garden. The radius of the circle is 4x. The side length of the yard is 20x. What is the area of the yard outside the garden? Write your answer in factored form. There's a circular garden in the middle of a square yard. The radius of the circle is 4x. The side length of the yard is 20x. What is the area of the yard outside of the garden? So we need to find this blue area. Write your answer in factored form. So just like before, you need to find the area of the big square, and we're going to subtract the area of the garden, which is the green. So here's what I would do if I were you. I would do 20x times 20x. And then we're going to subtract the area of the garden. But it's a circle. Do you remember how to find the area of a circle? What's the formula? If you know it, say it out loud. Oh, good. Pi r squared. Let me just write that up here. Pi r squared. And what's the radius here? It is 4x. So pi times 4x, that's the radius, squared. So I'm going to multiply this out. 20 times 20, 400x squared minus 4x times 4x is 16x squared. And then there's the number pi still multiplying it. And then I still have to write my answer in factored form. I'm going to look for a GCF. Does 400 divide by 16? Let me check. It does. 25 times. I can factor out a 16. Is there a common variable in both terms?
Yeah.
16, I just figured out on my calculator, times 25 is 400. I don't need any additional x squareds. Minus. I already have this times what? What goes here? If this was squared, it would be a difference of squares because that's a perfect square, but this is not squared. So I could only do a GCF factor, and this would be my answer for 23. I'm going to end your notes right there.